Thanks, Jonathan, for inviting me, and thanks to PSI for putting this thing together. And also, I see that there's a few familiar names on Zoom, so thank you everyone for coming. So first, I want to just start by switching to a simpler title because this is a lot. So basically, what I'm going to be talking about today is how we can observe energy cascades in the ocean using different sets of observations. In particular, I'll be focusing on surface drifters. So this is some work that I started doing when I was a postdoc at NYU with Jinhan Shi, who was also a postdoc at that time. And he's sort of the real theoretical foundation behind everything that we've done. And later we had collaborators who came in, Rafael Marino and Fabio Frascio, who are world experts in doing DNS simulations and looking at energy cascades and rotating stratified flows. So let me just jump in. So I was looking at Yohai's talk last week, and I got concerned for a second that Jupiter just looks really nice, and we don't have anything on Earth. Then I reminded myself that that's not true. And so what I'm showing here are two images from different parts of the ocean. On the left is near Finland, and basically both of these are natural color images. So no enhancement has been done. Like this is what the Earth looks like from space. And so this over here, what you're seeing are phytoplankton bloom that's taking place. And then the underlying surface ocean currents are stirring it around. And you can see all these complex patterns forming. There's this big eddy in the middle. There's another one there. You see smaller scale fronts that form in different places. And similarly, on the right-hand side, some of the white is clouds, but a lot of the white that you're seeing down here is sea ice, which also acts like a natural tracer and gets stirred around by the underlying currents. And you again see that there's all these beautiful patterns that form. And part of the research that I do is try and understand, why are these patterns forming and sort of how they form and how they evolve in time and what exactly happens to these guys. So stepping forward, let me show you this. Since we are talking about the surface ocean, here's a movie of what the flow in the surface ocean is doing. So this is a movie that was made a few years ago by NASA, and it's called Perpetual Ocean. You can find it online if you don't see it easily on Zoom. And so what's being visualized over here are the surface currents with the help of little particles. And each particle, as it moves around, its track is being plotted on the surface. So, and the track is over a fixed duration of time. So when you see long tracks or these big coherent structures like those eddies or sort of these kind of jets, those are regions where the particles are swirling around really fast. The places where you see shorter tracks are where the ocean's flowing slower. And basically what I wanted to point here is that there's just an enormous amount of variability that's present in the ocean. It varies depending on where you look. So this line is the equator, and near the equator, you see all these very large scale features on the order of hundreds of kilometers. When you move away from the equator, the size of the eddies changes depending on where you are in the ocean. For example, in enclosed seas, structures look different. Near western boundary currents, for example, the Kuroshio over here, you have this big massive jet that shoots off from near Japan. And on and on. Like we can keep looking at this movie for a really long time, and I hope that you'll go and do that online. It's really amazing that we can do this now. So let me sort of contrast the two visualizations that I've shown you. So the one on the left hand side is produced by an ocean model. The model is called ECHO2, which is a quarter degree model. So that means that the grid is about 25 kilometers. A spacing of 25 kilometers, which we often, in oceanic jargon, we call that as mesoscale permitting, which means that mesoscale in the ocean are scales that are about 100 kilometers, mesoscale permitting, because if you have a grid of 25 kilometers, you're barely just resolving things that are on the order of about 100 kilometers with that grid. And that is what you see. So you do see a lot of variability, but the size of this variability is on the order of about a few hundred kilometers. For example, this eddy in the Gulf of Mexico, which are sometimes also called loop current eddies, is about 300 kilometers, and you can see that forming. Versus the picture that I showed you at the surface, the size of this eddy, which I think I forgot to point out earlier, but this structure is about 30 kilometers in size. And so when we run simulations like the one on the left, we will never resolve anything that is happening at such small scales. And so these models will never see what's happening at such small scales. And so they are not, so basically, if you want to understand what's happening at smaller scales, we will need to go to higher resolution simulations or higher resolution models. And I'll show you an example in the next slide of that. So these are two snapshots from a global model, which was run at a 48th of a degree. So that's 2 kilometers. We would call this as sub-mesoscale permitting. So the sub-mesoscales are scales that are smaller than the mesoscales. And again, because the grid is about 2 kilometers, we can resolve structures that are on the order of about 10 kilometers. So we can barely start resolving eddies that look like this. And so in the sub-mesoscale permitting model, what I'm showing you is the Gulf of Mexico, because that's a region that I'll be focusing on in the rest of this talk. And I'm showing two snapshots. One is in the summer and the other one is in the winter. And what's plotted here in color is surface vorticity, normalized by the Coriolis frequency. And so when the values are bright red, that's Coriolis, that's a vorticity of 1, positive cyclonic vorticity. When the colors are blue, it's anticyclonic vorticity. And so the first thing that we see is that, again, like our movie, which was mesoscale permitting, we see large eddies, so on the order of a few hundred kilometers. But if you look closer, you start to see that there's also a lot of finer structure that is starting to emerge in these simulations. And we also see this very interesting behavior that in summer, there's all these finer scale structures. In winter, these finer scale structures sort of get enhanced, or they get more energetic. And the obvious question one has is that, how is this variability being generated in the ocean? And, how are these complex flows and structures sustained? We ask questions about, what are the flow dynamics or the dominant physical balances that are going on? Do the balances that are taking place at eddies that are a few hundred kilometers, are they similar to what happens in small scales, or are they, qualitative differences that are present? Then obviously the question is, how are tracers stored by these structures? Because we already saw an example of how phytoplankton forms all these interesting patterns. So, there's stirring going on. We can ask questions like, what are the characteristics of individual flow structures? How would individual filaments or fronts behave, and what would be the dynamics over there? And then one question that I'll be discussing through the rest of this talk is, how is about how kinetic energy is distributed across scales, and why that distribution exists, and how that is maintained. And one can also ask questions of, what are the large scale impacts of these structures? Are they just some wrinkles in the flow which don't really matter, or are they actually important for large scale oceanic flows or climatic events? And so I just came across this paper earlier this month, showed up on my Google feed, and these authors are arguing, I'm not an author, this is just a study that I read, they're arguing that large scale oceanic phenomena like ENSO do get affected by what the submesoscale eddies are doing. So clearly there is reason to study these scales further. So going forward, I know that some people over here may not be oceanographers, and I just wanted to introduce this one instability, which is called Bioclinic Instability, that we often think about in the ocean. These schematics and visualizations are from a paper by Jorn Kallis in 2016. So let's look at the schematic that's on the left. And this is roughly a mean state that exists in many places in the ocean. So what you're seeing in colors is the density field in a slice, in a depth versus meridional distance slice. And this density field is further highlighted by these black lines, which are some particular contours. In the ocean, we'll call them isopycnals. And basically what you see is that as you go deeper, color gets darker. Darker means denser in this context. And so the ocean is getting denser as you go deeper, but it is also getting denser as we move laterally. And so as we come from the left side to the right side, the ocean gets denser in that direction. And the reason to study this particular mean state is because we do see this present in the ocean. A combination of the fact that solar heating is differential, so it's warmer near the equator, cooler near the poles, in combination with winds can set up density structures in the ocean at large scales that that roughly behave like this. And in addition to those large scale forcings creating density surfaces that look like this, I'm also in this particular schematic, there's also a mixed layer that's been added in. So this is the region that's very close to the surface of the ocean that is well mixed. And so this is a region where the stratification is weaker. And that's why you see that the variability in density is weaker relative to deeper in the water column. And this deeper part is often called the pycnocline or the thermocline. So why is this state important? So this state is important because in this state, the system has some available potential energy, or it has basically some excess potential energy that is present. And the system does not like to hold on to that. And so any small perturbation that you give to this mean state, the system will use that perturbation to transfer the excess potential energy from the potential energy reservoir to the kinetic energy reservoir. And I should just point out that there's excess potential energy here because the natural state that the system would want to be in is a state where the isopycnals are flat. And so you have sloping isopycnals, you have this density structure, you give it a little kick in a perturbation, and that perturbation grows. And this growth is called Bioclinic Instability. And we can also estimate the characteristic scale at which this instability would grow. And it's roughly on the order of the deformation radius, which scales like this number, this formula over here, NH over F, where N is the strength of the stratification, vertical stratification, F is the strength of the rotation, and H is a characteristic depth scale. So for example, in this particular schematic, there are two depth scales. There is a depth scale corresponding to the mixed layer, and then there is another depth scale corresponding to the thermocline. And so if you take this state and put it in an ideal simulation and run it, what you will see in the very initial time is that you will start to see instabilities at two scales that correspond to these two depth scales, which correspond to two different deformation radii starting to grow. But very quickly, these instabilities or these perturbations that are growing, they start to interact with each other, and you eventually reach an equilibrated state that kind of looks like what you see on the right-hand side. So over here, you're seeing there are large eddies, there are small eddies, there's all these filaments, and it looks a lot like the picture of chlorophyll that I showed you earlier, or the high resolution simulation that I was showing you earlier. And so the main message here is that there is this natural instability that's present in the ocean. It's taking place at a few characteristic length scales, but the presence of nonlinearities can sort of fill up the other scales that are present with energy. And just as an aside, before I move to the next slide, I wanted to point out how we will study what's happening in scales over here. And usually that is done in spectral space. So for example, if you have some signal like this red line over here that varies in space or time, we call it UX, we can decompose that in using a Fourier transform into different modes. And once we have done that decomposition, each mode has a characteristic wavelength that would correspond to the length scale of that mode. And the nice thing about doing this decomposition is that we can write the energy as a sum of the energies that is present in individual modes. And so what this Fourier decomposition allows us to do is it allows us to write the total energy of total energy or kinetic energy of the system into the energy that's present in individual modes. And once you have done that, you can write down equations about how that energy in individual modes evolves in time, and also how the energy in individual modes interacts with other modes. And this interaction is often called the spectral flux. And so that is how we study these sort of complex nonlinear systems. So now let me come to this schematic that I took from the paper by Patrice Klein a couple of years ago. And what I'm showing here is a schematic of how this instability that I just described, how that is acting in the ocean, and what are the different energy reservoirs doing. And so basically you have large scale forcing that is going on, that is setting up the density structure that I showed earlier. Now this density structure is unstable to baroclinic instability. And so at about scales of 100 kilometers, which is roughly the deformation radius, 100 to 50 kilometers is the deformation radius of the oceanic thermocline, baroclinic instability kicks in, it transfers potential energy to kinetic energy. And sorry, I forgot to mention the top line is showing what happens to the potential energy reservoir, and the bottom line is showing what happens in the kinetic energy reservoir. And the lines between these two show how the exchange goes on between potential energy and kinetic energy. And the left side is large scales, and the right side is small scales. Okay, so now that we have that context, so yeah, there's Bioclinic instability that takes place on the order of about 100 kilometers, releasing potential energy to kinetic energy. And as that is happening, there are these eddies that form, and they can start to stir around the density field. And basically, that corresponds to a transfer of potential energy to small scales through eddy stirring. And then as this density field is being stirred to smaller scales, at scales of about 10 kilometers, which is scales of where fronts form, and also scales where instability in the mixed layer takes place, there will be another transfer from potential energy to kinetic energy, but this is at finer scales. And then as this energy gets transferred, this energy that has reached the kinetic energy reservoir can either get transferred upscale or it can get transferred downscale. But in rotating stratified flows, we think that a lot of the energy gets transferred upscale, because that's what simulations show us, that's what theory suggests. But there can be a small fraction that goes down as well. So we have the schematic. Does this happen in the real world? And so let's look at some observational evidence. So I'll be looking at observational evidence of what's happening in the kinetic energy reservoir. So what I'm showing here is a picture. It's a zonal mean. So the x-axis is showing you what happens as a function of latitude. So north is here, and the south pole is down there. And the individual lines that are shown are the yellow line shows the growth rate of the Bioclinic instability of the thermocline. The red line shows the deformation scale. And so the point being that the growth scale roughly corresponds to the deformation scale. And the blue line are observations of eddies from sea surface height fields, and they show you the size of the eddies. And so the first thing that you see is that the growth of the instabilities is taking place at small scales, but the eddies that we observe are significantly larger, about an order of magnitude larger. And so this is an indirect evidence that there might be an inverse cascade run. But we can also sort of do a little bit more and look at the spectral fluxes. So I initially talked about how we break up the energy into modes, and then we can look at how energy gets exchanged between modes. So that exchange is called spectral flux, and that's what I'm showing here from a paper by Scott and Wang in 2005. And what's plotted here is the spectral flux as a function of the wave number. And the way to read this plot is that when the values are so the zero line is right here. So when the values are negative, that means that the energy is moving from small scales to large scales, inverse cascade. And when the values are positive, the energy is moving to finer scales. And so what Scott and Wang found, they found this strong signature of an inverse cascade. What this plot is also showing is that likely energy is being injected at scales that are roughly here. So whenever you see a positive slope in this line, in these plots, that means that the energy is getting injected at those scales. So they found that there's an inverse cascade. They also found that there is energy being injected at scales of roughly about 150 kilometers in their observations. And then they found some signature of a forward cascade. But this forward cascade that or cascade to smaller scales that they found has been hotly debated over the last 15 years. And I mean, I think I can say that nobody really trusts that this is what is happening in the surface ocean. And part of the reason is because the data set that was used had a resolution of roughly about 100 kilometers. So anything that we are seeing close to that resolution is likely, can likely be corrupted. Also, they had to make assumptions. So what they were doing was taking the sea surface height field and converting that to velocities using geostrophy. And once we start to get to smaller scales, that assumption of geostrophy doesn't hold really well. So when you use geostrophy, you're not observing the full velocity field. And so this forward cascade that they observed is, maybe the best thing to say is that it's kind of suspect. And so we want to do more investigation to see if this actually exists or not. So let's look at more observational evidence of what's going on. So as I said earlier, satellites allow us to see what's going on up to scales, from large scales up to scales of about 100 kilometers. If you want to look at scales that are smaller, we have to look at in situ observations. And so this is a paper by Jorn Kelly in 2015. And what's shown over here is the power spectrum. So that is the distribution of kinetic energy across scales. The power spectrum's on the y-axis, the length scale is on the x-axis. Small scales are to the right and large scales are to the left. And these are plots for two different seasons. So the top is winter and the bottom is summer. And I know it's a little hard to compare these plots when they're sitting separately, but the best way to do that is use the gray lines as a reference because they are the same in the two plots. And so what we see in winter is that the power spectrum is close to this gray line that's on the top, while in summer, the power spectrum basically drops below the second gray line. And the main message here is that in winter, the scales that are smaller than roughly 100 kilometers, which is wavelength of 10 to the minus 2, become more energetic. And so in winter, there's more energy at sub-mesoscales, scales smaller than 100 kilometers than summer. And a similar observation was made. So this observation comes from a region that's near the Gulf Stream. A similar observation was made in the North Pacific, close to the Kuroshio by Bochu et al. In 2017. And basically, they're looking at the kinetic energy spectrum as well. One extra step that they have done is they have decomposed the velocity field into a balanced part and another part that is wave-like or unbalanced. And basically what they're seeing is that when you look at the balanced kinetic energy, that there is more of it in winter, which is the blue line, than in the summer. While when you look at the wave component does not change very much between the two seasons. And so this is very interesting confirmation, and it's starting to give us clues of what's happening at scales that are smaller than what Scott and Van observed. We're seeing this nice seasonality. So what's going on over here? And so I like the schematic that is by Hemant Khatri in 2021. And let's step through this for a second. So basically what they're suggesting is that let's start in the summer. So again, the blue line is the power spectrum and power spectrum of kinetic energy plotted as a function of wave number. And so what this suggests that in summer, we have a certain distribution of energy that's present. This has a certain power law, k to the minus 3, which just for reference corresponds to an entropy transfer. So what's happening in the summer is that there's this Bioclinic instability that's taking place. Most of the energy gets transferred to larger scales in an inverse cascade, and the entropy gets transferred to smaller scales in an entropy cascade, and you get a power spectrum of k to the minus 3. Now, as you start to move towards autumn, remember this schematic that I showed you earlier, right? So there was a mixed layer that was present at the surface, and this mixed layer had its own instability scale associated with it, which was smaller than the Bioclinic instability scale. And so at the mixed layer instability scale, because mixed layers are getting deeper, they are starting to have more available potential energy. That available potential energy starts to get released. And so you're starting to inject energy into modes that are smaller. And as you do that, now you have energy sort of pushing this power spectrum bump a little bit higher. And as you wait a couple of months more, you get to late winter, when the energy that has been injected at this mixed layer instability scale has basically painted these scales. And now you are getting a power spectrum that is more energetic. It is a little bit flatter. So it's being bumped up, similar to what the observations are showing us. So yeah, and so this is, in some sense, this is an indirect evidence of what the energy transfers are doing. So we are basically looking at the effect. So we have certain energization and energy transfers that are going on, and we are looking at the effect of that in the energy that's contained in the modes or in the kinetic energy reservoir. We can also look at this directly using the spectral transfers. And so the top plot is showing spectral transfers in a simulation that was run by Takaya Yoshida a few years ago in winter and summer. So blue means that the energy is being transferred to large scales, and reddish colors means that the energy is being transferred to small scales. And so basically what they find is that in winter, there's a strong inverse cascade because the mixed layer instabilities are getting stronger. In summer, this inverse cascade gets weaker. But if you zoom in near the surface, what you also see is that there's the presence of a weak forward cascade. And the strength of this cascade in these simulations is on the order of a few percent, or maybe 1% or 1 to 5% of the strength of the inverse cascade. But we can also look at other simulations. So this is a study by one of my collaborators, Rafael Marino, and came out in 2015. And basically what they did is they took a direct numerical simulation. It's a very ideal triply periodic domain. And what they showed is that as you change the parameters of this ideal simulation, you can change the strength of how much of the energy gets cascaded to smaller scales. So basically under certain parameter regimes, you can have as much as 50% of the strength of the inverse cascade, that much energy going to smaller scales. But then if you increase your, as you decrease your stratification, the strength of this forward cascade gets weaker. So all of that is really nice. And it is giving some support to this schematic. But the thing that is missing so far is that we don't have any direct observations of this forward cascade. And we also don't have any direct observations of the energy injections that are taking place due to mixer instability. We have seen that in observations that the power spectrum at small scales is getting stronger, but we did not actually observe that, at what scales was the energy injected into that. And simulations are suggesting that there can be a forward cascade, but again, we have not made any observations of that because Scott and Wang could not go down to scales where these things are likely coming in. So that would be after this long introduction, that will be the topic of this talk. We want to discuss questions about, do these energy transfers exist? If they do, how strong they are, if there's a seasonal variation to that. And one can also ask about the geography of that, but that's not something that I address over here. So to do that, let me just pause this video. So basically what we need observations that are making, that are telling us what the velocity field is doing at really small scales. And that is very hard to come by in the ocean. And the way that we are going to go about doing that is with the help of surface drifters. So these are instruments that flow at the surface of the ocean. And as they go around, you can track their position using GPS. And if you release a bunch of them together, then you can start to see what's happening at the scales that are really fine. You can put in 2 or 3 together and you can start to see what's happening on the order of tens of meters. And the drifters that I'll be talking about were provided by the Carthe Consortium, which was this amazing study that was done in the Gulf of Mexico following the BP oil spill. So what I'll be showing you on the left-hand side is one study that was done in summer of 2012, which was called GLAD. And on the right side, a study that was done in winter of 2016, which was called LASER. Each little line that you see over here corresponds to the track of one drifter over 5 days. Little red colors are the current location of the drifter as it moves around, and black dots are where they were released. And so basically you see that these drifters are put in, they are moving around with the flow. There's all these interesting patterns that one is seeing. For example, you can see these oscillations going on the order of timescales of about a day, which are the inertial oscillations. You see that there are some of them getting stuck in really big eddies. Let me start again. And some of them get separated out very initially. I mean, there's a lot of structure that's present in these observations, and these will be the focus of the rest of this talk. And so here is a full image of what these drifters did over the 3-month period that they were in. So both these experiments were roughly 2 to 3 months long, and these are what the tracks did over that time. For the analysis that we'll be doing over here, we'll be focusing primarily in a region that's in the northeast Gulf of Mexico. And that's done just because we want to stay in a region where the dynamics are relatively homogeneous over that. And also not shown in this box, but for the analysis that I'll be doing, I only consider the tracks that are in waters deeper than 500 meters. So because we are asking questions about what's happening in the deep ocean rather than the continental shelf. So let me step forward. So earlier I showed you that we can do this nice spectral decomposition of the flow and study things like how energy is distributed, how energy is getting transferred across scales and such. This is a really great method. The problem is that when it comes to observations that are made using drifters, or actually a lot of ocean observations, which are collected using scattered platforms, we can't apply this anymore, at least not in the conventional sense, because this method requires us to have data on a uniform grid where you can do Fourier transforms and such. And so this method is a little bit out of the picture for our data set. Instead, what we can do is we can go to, instead of spectral space, we can go to real space and start looking at what is happening, basically start looking at 2-point correlations. And so, for example, writing over here, the covariance, which is basically the covariance between 2 points, one point X and another point that is a distance R apart, shown over here. So you measure the velocity at one point, it's U, at some point R apart, it's U prime. And you can start to see how these things are correlated with each other and use that to make some sense of how things vary over spatial scales. And the reason we want to go through this avenue is because when we have surface drifters, they are essentially telling us the velocity, the strength of the velocity at 2 points that are a certain separation apart, but in a very scattered sense, because we don't control where the drifters are, they just go where the flow takes them. And I'll show you why this method, how this method relates to the spectral method. But before I go there, I like this schematic because it helps us understand that why what we are doing here, looking at 2-point correlations, why that tells us anything about scales. And so, we can envision the ocean, just for a schematic purpose, as a sea of eddies. And so you have these big eddies, you have little eddies sitting inside those big eddies. So if you look at points that are far apart, like this big red line connecting 2 points that are far apart, we are getting information of what the big eddies are doing. And as we start to decrease the length of that vector, we start to see what's happening on the finer scales. Using these, and so that is why it tells us something about the scales. And we can actually show this mathematically, that there's a relation that exists. And I'm sure a lot of you already know this, but if you look at the covariance is directly related to the kinetic energy spectrum, which was this quantity over here, which was the decomposition as a function of modes, as a Fourier decomposition. And then for the purpose of this talk, instead of looking at the covariance for some practical reasons, we look at quantities like structure functions, which also, let me step back. They are, instead of just being defined as the correlation between those 2 points, it's defined as the velocity difference between the 2 points. And that itself is related to the covariance because, for example, if you look at delta U square, that has 2 terms that correspond to the energy at the individual, or the velocities at the individual points, and then it corresponds to the correlation between those 2 points. We can also look at higher order terms. So this was delta U velocity difference squared. We can look at quantities which are like velocity difference cubed. And the reason we want to look at those cube quantities is because the cube quantities relate to the spectral flux, the FK, which I plotted earlier from the Scott and Wang paper. And let me just get some water and then we'll continue. So we have these quantities that we call structure functions. They exist in different orders: second order structure functions, which correspond to velocity differences between 2 points squared; third order structure functions that correspond to velocity differences cubed. The second order structure functions are related to the energy in the system, and the third order structure functions are related to the spectral transfers that are taking place in the system. Now, going forward, I'll be focusing entirely on third order structure functions for this talk. But I just want to mention that the analysis that we did, we have also looked at second order structure functions and basically found things that are similar to what people found near the Gulf Stream and the Kuroshio, which is that the amount of balanced energy present in the system gets enhanced in winter. And so basically the system is more energetic in the winter, and it's largely in response to the increase in balanced energy. So let's look at what the third order structure function does. Oh, sorry, I forgot this slide. Before I go into what the third order structure function is doing with our data set, let me just show you a couple of results from ideal setups. So, 2 ideal setups that we often think about. One is 3D turbulence. So this is turbulence in a box. There are no boundaries, and there's some characteristic length scale where you're energizing the system, and then this energy gets cascaded from that forcing scale down to the dissipation scales. And what was shown in, I think, 70 years ago now, is by Richardson, was that in that system, the third order structure function, which I'll be referring to as V going forward, has this exact relationship to the energy that is injected into the system, which is the same as the energy that gets transferred across scales, same as the energy that gets dissipated, as this exact relationship, the 4/3 law. So the third order structure functions minus 4/3 epsilon r. It's important to remember here that this is not a scaling argument. This is an exact formula that appears for the system. And similarly for two-dimensional turbulence, which is basically turbulence in a slice flow, where we have an entropy cascade and an inverse energy cascade, similar formula appears. So there is VR depends on eta r cubed, 1/4 eta r cubed, where eta is the entropy transfer rate, and it is 2 epsilon r when there's an inverse cascade rate. And another thing to note here is that in the forward energy cascade scenario, this quantity is negative, and then in the inverse energy cascade scenario, this quantity is positive. And so these are some ideal relationships that exist for this quantity. So let's step forward. So now let's look at what the third order structure function is doing with the data set that Karth gave us for GLAD and laser. Going forward, GLAD will be shown mostly as color red because it was summer, it was warm, and laser will be shown as blue colors, winter blue. And what's plotted over here is the absolute value of the third order structure function as a function of length scale. Small scales are now on the left, large scales are on the right. And both the data sets are shown here. And then the dashed thin line in the back is corresponds to a power law of r to the 1, or basically a linear slope. And so the first thing that you see about this data set is that V, or third order structure function, scales linearly as a function of spatial scale, roughly. The second thing that you observe is that at scales smaller than a certain scale, the values of, I should point out that where it's a dashed line, that is values that are negative, but on a log scale, I've plotted the absolute value, right? So wherever it's a dashed line, the values are negative. So below a certain length scale, the values are negative. Above a certain length scales, the values are always positive, and the scaling is linear. And this is something that has been presented in a number of papers, starting by a paper that I wrote during my PhD in 2016, and then ones that followed from the Karth group. After that, some really nice papers by Andrew Kolge and Jenna Pearson, who I think is on the talk here, and then more recent ones by Berta. And so this result has been shown in a few places, and the way the interpretation usually goes is that we look at this, we look at these ideal formulae that we have for simple systems, and we say that, okay, when we see negative values, that must be suggestive that energy is cascading to smaller scales. When we see positive values, that is suggestive that the energy is cascading to larger scales. But there's a couple of problems with that. One, that these ideal formulae are for very simple systems, and also they only apply over inertial ranges. And so we want to do a little bit better than that. And we did that in our study. And this is based on theoretical work that was done by Jin Han when he was a postdoc at NYU with Oliver Buehler. And so what they did is they looked at this formula, right? So there's an exact relationship between V, third order structure function, and the spectral flux F. And it takes some complex form with a certain order Bessel function in it, and there's this infinite integration that's taking place in it. So what they did is they took that and they basically discretized it. So they said that, okay, we know V, we want to find what F is. And in their particular case, they were looking at more sort of theoretical scenarios where you have a certain F that you impose analytically, and then you start studying what corresponding V does. But basically the story goes is that we take F, we discretize it using a set of basis functions. The set that is chosen is physically motivated, and it looks like this. So there is a piecewise constant, which corresponds to epsilon u. And the interpretation for that is that this is the energy that gets cascaded to larger scales. And then there is a summation of these epsilon j's at a series of wave numbers, kj's. H is a step function. And so basically you have epsilon j at 1 kj, and then you will have epsilon 2 at k2, and so on. So this, you can use this basis function to represent, roughly represent any sort of function that you want to give f. And once you have this, you can plug this relationship in here, do the integration analytically, get this discrete form. And so now one thing nice that has happened is that, well, you've gotten rid of your integration. The V is represented as a combination of certain parameters or unknowns, epsilon u's and epsilon j's and kj's. And once we have this form, what we can do is that we can go to our data set where we have estimated what V is, try to invert this and find out what the corresponding epsilons are. And the way that we do that is, because this is just a set of linear equations, the way that we do that is by using least squares. But if you just go about doing it using least squares like this, or if you just sort of naively try to invert this relationship, basically what you get is just a bunch of noise. And the reason for that is that any sort of small errors in your estimates of V in this form get amplified, and that's all you see. And so to avoid that error growth, you need to make some assumption or do some regularization of the system. Put some, the way that I think about it is put like a physical constraint on the kind of values that these epsilons can take. And the assumption that we made was that we assumed that all epsilon j's are positive. And it is a very critical assumption, and it is physically motivated. And what it is implying is that, if you remember back to the schematic, what we are assuming is that by epsilon j's being positive, we are only allowing a transfer from potential energy to kinetic energy. So if in the real world, if there is any transfer that goes from kinetic energy reservoir to the potential energy reservoir, our method will not be able to track that. Okay, so this is a key assumption, but we have to make it to make some progress. See something in chat, 5 minutes remaining. Yeah, okay, I think we'll be done in 5 minutes. Okay, so let's see what happens when we go through this least squares procedure with this physically based regularization. So let me introduce these plots. So what I'm plotting here again is the third order structure function, but now the y-axis is not a log scale anymore. And because it's not a log scale, if I just plotted V by itself, since it varies over a large range of magnitudes, it would be very hard to see that. So what we did is we normalized that by R, because we knew that V roughly scales like a linear power law. So if we normalize that by R, we can visualize it very easily. And this is for, again, red GLAD data, blue laser winter data. And again, we see that there are a certain range of smaller scales where V is negative, and then there are larger scales where V is positive. Also, the nice thing about bringing this to a linear scale is that it becomes much easier to show the error bars that are associated with it, especially when the sign changes, because that is very complicated to do on a log scale. And so we see this nicely. And then the dashed black line is basically the fitting that we get using our least squares. So using our least squares, we're trying to fit V, which is the line, the colored line. And then when we fit it, we get the dashed black line. So the first thing that you notice is that, it roughly fits the structure pretty well. It is not picking up every single curve and bend in that. And we kind of wanted that because we did try to do this without any regularization. And when we do that, every single curve and bump in this line can be fit. And then the results that we get are a little bit harder to make sense of. And I can say something about that a little bit later. But basically, we impose this regularization. You can think that what it has allowed us to do is, basically pick the sort of the 0th order structure that's present in these observational estimates. And so so we are fitting, but we're not overfitting. Every synoptic variability. Let me show you. Okay, so this was the V. Now the next column that has shown up are the epsilons. epsilon j's, which is a measure of how energy is getting transferred into the kinetic energy reservoir. First note that I've gone from separation scale R to wave number scale here. So the scale has turned around. So on this axis, large scales were on the right. On this axis, large scales are on the left. And again, summer on the top, winter at the bottom. And let's focus on the summer one. So what we see is that there's this energy injection that's taking place at larger scales, roughly on the order of about 50 kilometers. And then we see injection of energy taking place at smaller scales, which peaks at roughly about a kilometer, but it has, it's sort of broadband. We know from our knowledge of the stratification in this region that the deformation radius is about 50 kilometers. The interior deformation is about 50 kilometers. And in summers, when the mixed layers are shallower, the mixed layer deformation radius would be roughly about a kilometer. And so these energy injection scales, I interpret them as energy being injected at roughly the mixed layer deformation radius and the interior deformation radius. Then when we go to winter, what we see is that the energy that was getting injected at the interior deformation radius, the strength of that stays about the same, and also the scale where that energy injection is taking place stays about the same. But if you look at the smaller bump, that has moved to larger scales. So now it's peaking at roughly about 5 kilometers. And also the strength has increased. And again, if we try to understand this with, try to interpret this based on what's happening in the mixed layer between seasons, you can fit that story to this, thinking that, okay, in winter, the mixed layers got deeper, and because the mixed layers got deeper, there was more available potential energy to be released. And because that was the case, now that more extra APE is being released into the kinetic energy reservoir. And once we have this, we can go and look at what the spectral flux FK looks like. And again, it's shown over here. And basically in summer, what we see is that at scales larger than about a kilometer, there's energy that's getting cascaded to larger scales. And at scales smaller than about a kilometer, energy gets cascaded to smaller scales. So you're seeing a presence of a forward cascade. And in winter, the shape stays the same, but quantitatively things change. So first, we see that the strength of the inverse cascade is the same between summer and winter at scales above about 50 kilometers. But the strength of the forward cascade has increased in magnitude by a factor of about 2. Yeah, about roughly 2 in winter. And also the place where the forward cascade is becoming more dominant, that scale has also shifted to slightly larger scales. And I find this very, very fascinating, because this was the picture that our simulations were building for us. And now we are starting to see this in observations. And also the other interesting thing is that, we're starting to see some things that, at least in this set of observations, which has its own set of biases and it's everything that comes with any observations. But at least in these observations, the forward cascades are quite strong. They are in strength, about 25 to 40% the strength of the inverse cascade. I finally want to make one point that I'm guessing some people over here would be thinking about. And that is that we injected a certain amount of energy at the mixed layer deformation radius, or at this small scale, which I think is close to the mixed layer deformation radius. What fraction of that energy gets cascaded to small scales? And so all of that energy does not go to small scales. Actually, a large part of the energy that's getting injected here is still getting cascaded to larger scales, but some fraction of that is getting cascaded to smaller scales. And the fraction that gets cascaded to smaller scales is more in winter than in the summer. So I want to conclude with that. So we started out with this beautiful image of what phytoplankton blooms were doing in the Baltic Sea. See all these small patterns. We want to understand why these patterns form. And one of the questions that we asked about that was basically, these patterns are forming because of some instabilities and nonlinearities in the system. Let's understand how these nonlinearities are transferring energy across scales. And so we conclude by saying that we're presenting observational evidence of a dual energy cascading to small scales and large scales. And as far as I know, this is the first observational evidence of this. Of course, like any other observations, there will be caveats associated with this. Biases in the observations. Are these drifters uniformly sampling the flow? Are they sampling convergence zones, which might have stronger forward cascades more or less. There are questions that remain about that. We found that energy was injected in the system near scales that roughly corresponded to the interior deformation radius and the exterior deformation radius. There was a seasonality, a seasonal modulation in the scales where this energy was being injected and the strength of the energy that was being injected in. Particularly in the winter, there was more energy being injected at the exterior deformation scale. And finally, what we found is that in these observations, about 25 to 40% of the energy, depending on the season, 25 to 40% of the strength of the inverse energy cascade, that gets cascaded to smaller scales. And I want to finish with that. For people who are interested in reading the paper and some movies associated with these data sets, can screenshot this or use your phones to look at these links that I have. This is the one for the paper. I believe this one will take you to a movie of the high resolution simulation. And this last one will take you to a movie of the nice drifters that Karthik gave us. So thank you. And if there's any questions, comments, happy to discuss.
Great, thanks so much, Dhruv. That was really wonderful. Let's hear some questions for Dhruv. And just to keep things organized, if you could raise your hand or say that you have a question in the chat, let's do it that way. Herman, you have a question? No? Okay, James, you have a question?
I was just going to comment that this was a lovely talk, and I especially appreciated how you introduced terms which, all of us who've been doing this for a while should know, like radius of deformation and Fourier transform. I have members of my GFD class listening, and I very much appreciated the care with which you took to introduce all of the concepts. So making the talk very accessible. Thank you.
Great, thank you, James. Emma Khatri, you have a question?
Oh, hi. Thanks for great talk, Dhruv. That was really nice. I have just a small question, just based on last figure you shown here from summer and winter FK plots. When I was under the impression, at least, like when we decompose the spectrum into divergent part and the balanced part, we generally see in the summer the relative contribution of the balanced part, the divergent part tends to be more than in winter. And in looking at that, we thought that maybe the forward caster tends to be stronger in a relative sense in summer than winter. This picture basically shows the opposite. Can you really comment on that? Why does it happen? Or
yeah, so that's a good question. So something that I did not show, which I did mention, right? We looked at the second order structure functions, and for this data set, we find the same thing, that the strength of the divergent motions is stronger in summer relative to the winter. So why this is happening, I don't know. The simple answer is that. My interpretation is that it's, well, the simplest one could be that, there's just a certain bias that's associated with the data set, and maybe we should not try to overinterpret this. But putting that one aside, what we do find in the winter is that the balanced part of the flow is getting stronger. And it is possible that the forward cascade that we are seeing is largely associated with the balanced part of the flow. So we have stronger divergent motions in the summer, but a lot of them might be wave-like because inertial oscillations are also much stronger in the summer in this data set. And maybe those inertial oscillations are not having a very strong reaction on or a very strong impact on the cascade. So most of the divergent flows that we're seeing are IOs or near inertial waves. And then those are, they're just an energetic signal, but not interacting with the cascade itself. And the cascade is due to the balanced part of the flow, which gets enhanced in winter. And because it's a more energetic system, the Rossby number grows a little bit and or with strong increases in strength a little bit. And so then you can start to pump a stronger forward cascade. Maybe that's what's happening. Yeah.
Great, thanks.
The next question that I saw was from Mara.
Yeah, thanks. This is a really great talk. It was really interesting. I'm glad I got to see it. I was wondering, you mentioned the bias sampling briefly in your conclusions. I was wondering if you have any thoughts on how the distribution of drifters, oversampling, and convergence reasons might be influencing your results.
Right. Yeah. I very roughly touched upon that because I didn't want people here, others to get upset that I did not mention this. So one of the sort of the big conclusions that came out of this data set was that we saw these drifters, or not we, but people who Karth's team saw these drifters go into convergence zones. And then there have been studies since then showing that these convergence zones might be regions of enhanced forward cascades or enhanced dissipation. And so we might be oversampling that. And that can definitely be impacting the results that we're seeing. It's possible that we are seeing a forward cascade that's a little bit too strong because we are oversampling these convergence zones, which are associated with fronts and so on. So yes, that is true. As far as what can we do about it, I don't know of anything that we can do about it at the moment. Like, we recognize that such a bias exists. We can go to simulations and where maybe a forward cascade is present, put in drifters and see how much stronger that is, that bias, or what the strength of that bias is. But we don't have simulations that are, such high resolution that we can then start to say that, okay, we have a certain bias, maybe we need to reduce the fraction by 20% or something like that. But it's possible that in the next 10 years, we would figure out how to get rid of these biases. But at the moment, I don't know of methods to do that.
Great, thank you.
All right, great. Thank you. Thanks again, Dhruv, for a great talk. And thanks to the folks who asked questions. It is the top of the hour, and I'd like to keep things on schedule. So I suggest that we end the official talk now, and we'll have a recording of this available. But if anybody would like to keep chatting, we'll stay here on Zoom and continue the discussion for a little bit.